Okay, we'll go ahead and get started with a couple announcements. So your exam 0 opens today on zip grade. So that'll be a review of some general chemistry stuff and your understanding of how structure is communicated. So by now you should have logged into your zip grade account to know that your codes work. The exam opens after lecture ends today. You have 24 hours to complete it, so it'll close tomorrow at 12:15. It's 30 questions, multiple choice, A, B, C, or D. When you get to the last question, please review to make sure that you've answered all the questions and then submit it. Please make sure you submit it. If you neglect to submit it and then you send me an email saying you did the work but it didn't submit, I have no record of that. So please ensure that you do that. The scores will be viewable in ZipGrade sometime tomorrow afternoon, so you can log in and you'll see your answer sheet scored. I have to manually move the scores from ZipGrade into Canvas, and I don't want to bore you with the details of that, but that'll be later this week or next week sometime. But you should also download the Excel file that's in Canvas so that you can keep track of your points. And again, that will kind of show you your grade in progress as you fill in those cells. Any questions on that? Yes.
Will there be bonus questions on this test?
There's no bonus questions on the test. Any bonuses that happen will be in class during lecture period, so you have to be here for them, or they'll be online, and that stuff will be communicated throughout the semester. Yeah.
Is there any time limit when we start with the application by a certain time?
There's no time limit set once you start it. So, I mean, the window's 24 hours, so you have to get it done within that time. But there's no 60 minutes or 75 minutes once you start. So again, as I said, you probably don't want to start it today after class and then leave your browser open for like 12 hours because something might happen to your responses. I don't think it auto saves things, so if you're going through and your browser closes or your window closes, it's probably not going to save your in progress stuff. So just make sure you're aware of that as a backup plan. Yeah.
Would it possibly auto-submit as
I have it set to auto submit at 12:15 tomorrow. Do I know if it does that? No, I don't. Again, as the instructor, I have my view of this stuff, but I don't have any student accounts, so I don't know if it does that or not. Okay, so let's recap what we left off on. We were building these structures of hydrocarbons, specifically the alkane functional group. As we'll learn today, there's a couple different subclasses of hydrocarbon functional groups whose names all kind of seem the same, but they're not. And the name does inform us of the bonding pattern of the carbon atoms that are present. So we started with the carbon count 1, 2, 3. We went through methane, ethane, and propane. And the structures are shown here on the slide. And then I made it a point to talk about this way of sort of classifying things over here within the square bracket, I have 13C, 1H, and then the ratio. Because this is class is organic chemistry, you can assume that every molecule is going to have carbon and hydrogen. In Module 2, we'll deal with figuring out if there's any other elements present in the molecular formula.
Excuse me. I have a question about, on that third picture, you have I was having a little bit of trouble the other day understanding the brackets and parentheses, and I see that you haven't highlighted which number is which, like the dots, and I was wondering what the first two meant.
Okay. So the question is basically, what do those numbers in the square bracket mean? And conceptually speaking, what we're doing now is laying a foundation to understand NMR spectroscopy. And we'll learn more about that in Module 2, but NMR tells us basically the unique number of carbons or hydrogens in a molecule. So as we see for propane, the molecular formula is C3H8. There's 3 total carbons, but in the way of reporting this, that first number there says 2, that's associated with the number of unique carbons. So while the molecular formula has 3 carbons, only 2 of them are unique. And the reason for that is due to an element of symmetry. So we have 1, 2, 3 carbons total. If we draw a mirror plane down the central carbon, carbon 2, we see that carbons 1 and 3 are the same. So that reduces the number of unique carbons from 3 to 2. The second number, and I'll say this now, it'll be more clear in a couple weeks. Carbon is the easiest to understand. Protons get a little bit more difficult when we start talking about the ways of detecting them with NMR. So the second number is the sets of hydrogen. So there's 8 total hydrogen, but there's 2 unique sets. So carbons 1 and 3 each have 3 hydrogens attached to them. That's one set. The number in the parentheses 6 corresponds to the number of hydrogens in that set. We have a second set, which is highlighted in the green here. That carbon 2 has 2 hydrogens. So there's 2 sets, and therefore we have to report 2 numbers, and that's the ratio of the hydrogens in that set. So if we add those numbers together, 6 plus 2 is 8. That gets us the total hydrogen count. So that's part of the rules of reporting or classifying the structure according to these numbers. And why am I introducing this now? For a couple reasons. When you run a chemical reaction, like if you read your textbook, you'll read about reactions. Starting materials are treated with reagents that go to a product. But in reality, that seldom happens. You get products, so you get more than one thing. And so how do you figure out what those things are? We use spectroscopy. Those are these analytical techniques. We use instruments to figure that out. So the reason we want to understand this now is, given a molecule, how can we describe every possible thing about it that we can? So that's just my way of organizing NMR data. So what do these numbers actually mean? When we start seeing data, like this first thing is C13, so carbon. When we look at carbon NMR, that's telling us the spectrum of that is going to show two signals. The proton NMR is going to show two signals. And then there's this thing called integration. Those signals will integrate to 6 and 2. But for now, I'm just calling it a ratio. So that's carbon count 1 through 3. And I, with 100% confidence, can tell you for methane, if you're given 1 carbon and 4 hydrogens, there's no other way that you can construct that molecule other than what is drawn. The same for ethane and propane. So the problem that exists as we move up to carbon count 4. So for 4 carbons, the molecular formula will have 10 hydrogens. The problem now is, within that molecular formula, there's the possibility of drawing more than one structural formula. So those are called constitutional isomers. They have the same molecular formula, but the connectivity of the atoms, in particular the carbons, can be different. And so the reason we want to do this sort of classifying is that they have the same molecular formula, the same molecular weight. I've given you the name of one of them. Will the other one have the same name? And then will these values here be the same? So we have to figure that out in order to communicate the structure of these things so we know they're different. So with C4H10, there's 2 isomers. One of them is called butane. And furthermore, I'm going to call that a linear isomer. That'll become a little bit clearer as we start drawing some things. But then there's also a second one, and that one's branched. So when I use those terms, let's think of the carbon backbone as a path. So if the path is linear, there's no points at which you can break off and turn right, left, or up or down. So let's go through this exercise where we convert C4H10 into these structural isomers. I'm just going to start by saying linear, and that's how we'll sort of classify this. For any molecular formula, and again, C4H10 only has 2, but as we go up in carbon count, the number of possible isomers increases pretty fast. So when you're figuring these out, you want to do it in a very logical manner. So by linear, I mean we're going to take all the carbons, just bond them in a straight line. So C, 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 C. That's linear. And then we evaluate each carbon, count how many bonds it has, and then anything that's left over, we shove in a hydrogen atom. So that molecule is called butane. So when we look at butane, how many unique type of carbons are there? So there's going to be 2. I'm just going to put some subscripted numbers here so that you know what I'm referring to. And we're going to use a lot of different numbers for different contexts in here, and I'll try to explain what they are and maybe use different colors for them and stuff. So there's two unique type. So I'll say C1 is equal to C4. C2 is equal to C3.
Why don't we worry about the ratio of the partners?
The ratio.
So like, why don't we write 2 and then in parentheses 2, 2?
So the question was, you know, in relation to this sort of reporting of things, why doesn't carbon have that same ratio? I'll give you the brief explanation and then I'll explain it more in Module 2. Again, we're laying the foundation for interpreting spectral data, and that tells us what a compound is. You see these numbers here are odd. That allows us to see them in NMR, and they have to be odd based on some nuclear properties. But if we look at the isotope abundances of these things, hydrogen or proton is pretty much 100% abundant. Carbon-13, which is the NMR active nucleus, is 1.1% abundant. So it's not really there a whole lot, but that's what you see by NMR. Since proton is 100% abundant, some other stuff happens that makes these spectra look a lot more complicated than carbon. Carbon NMR, the data occurs as a single line. So we don't really need a ratio for it. When we look at proton, the signals appear more complex, and therefore we need the ratio. So one other thing I want to point out about like molecules when we're talking about them are some nomenclature things that are pretty common, you know, rather than saying carbon 1 or carbon 3 or something like that. And we'll learn the formal nomenclature rules. We kind of have to know where on a molecule something is, like directions. So carbons 1 and 4 have 3 attached protons, and they're referred to as methyl groups. So methyl groups. Carbons 2 and 3 have 2 attached protons, and they're called methylene. Apologize for my sloppy handwriting. So methylene. And as we learn more reactions, you know, I'll converse with you and say, these reagents will act upon the methylene group on this carbon backbone. So then you kind of have to know what that is. It draws your eye to it, and then you understand that, okay, it's that carbon or that CH bond that's going to be changed. Yeah.
So the name changed based off the number of protons attached, right? Is that consistent?
Yes. So methyl, methylene, and then a CH, I'll tell you. A carbon with no hydrogens doesn't have a special name for it, really. One thing I want to show you as well before we move on to the branched one, I'm not going to continue drawing molecules this way because it just takes forever. So we're going to shorthand that to just a line drawing. And so this thing will then become that. And let me point out sort of the end here, the terminus. That is a carbon atom. It's showing a sigma bond to carbon 2. So you're seeing explicitly one bond. 4 minus 1 is 3. So that has 3 hydrogens attached to it. And typically with carbon, we do not explicitly show hydrogens. You have to understand from the Lewis dot rules they are there. Anything else, heteroatoms, nitrogen, oxygen, phosphorus, sulfur, those we explicitly show H. But for carbon, we don't. So when you look at something like this, you should be able to count the carbons, count the hydrogens, come up with the molecular formula. So I said there were 2 structural isomers. The first one's linear. I put the number 4. There's no other way that you could construct a linear isomer with 4 carbons and 10 hydrogens. So what is the logical way of doing this? We're gonna drop down the longest chain. So see, this is the longest chain here, 4. We're going to chop a carbon off, put the longest chain as carbon 3 now. So 4 carbons was butane. We're at 3 is the longest chain now. So this is going to be a derivative of propane because propane is 3 carbons. Now we have 1 carbon left to deal with to get to our desired molecular formula. On what carbon do we have to put the remaining 1? Why? So if you put it on 1 or 3, you're just making butane again. So by logic, it has to go on carbon 2. So without me drawing the hydrogens in yet, how many unique carbons does this molecule have?
3.
We got the 2s versus the 3s. Let's do a West Side Story fight here. It's 2. So again, the way things are drawn might appear to trick you, but you have to look at the connectivity. Carbon 2 has 1, 2, 3 carbons bonded to it. All of those carbons have how many attached hydrogens? 3. And then this one has 1. So there's 2 unique carbons, 2 unique sets of proton, and then what's the ratio of the proton sets? 9 to 1.
And you always do the largest number first, the ratio.
Yeah, that's just my way of doing it. So let me write this down. This was 2 to 2. I guess we didn't put these numbers in yet, but 6 and 4. That's for butane. So for the branched one, we had 2 unique carbons, 2 sets of hydrogen, and that was 9-to-1. So you can see that because of those numbers being different, we've figured out a way of classifying the constitutional isomers as being different. But now, what about the name? I said it has to be a derivative of propane. So I heard some variations of the correct answer here. Propane is the parent. On carbon 2, there is this group which is called a substituent. This is the main path. Anything off the beaten path is called a substituent. So that substituent is on carbon 2. It's 1 carbon. It's called a methyl group. So this is called 2-methylpropane. And so that's how we would draw it. And now we have that central carbon 2. That's a CH group. That's called methine. So I kind of said this before, but organic chemistry it's sort of like recursion. You have to know it to learn it and learn it to know it, that sort of thing. What you'll find is, a textbook is ordered in a linear fashion of topics and subjects and stuff. But as we proceed through lecture, I'm going to introduce a lot of different things so that we can start communicating and understanding structure. So this stuff here, the ratio, again, that's for NMR, which is chapters 14 or whatever. This stuff here, that's nomenclature, that's chapter 3 or 4 or something. So we have to hop around a little bit and introduce these things bit by bit to understand how structure is communicated. So other than that, we can't do any more. We can't go down to a 2-carbon chain and then start shoving 2 more carbons in, because you're just going to make one of these that you already made. Any questions? So let's put this to practice and see if we understand it. We're going to go up now to pentane. So once we get to pentane and above in carbon count, so there's a line between the T and the A. The ANE tells you that it's an alkane. And now the front part of that tells you the number of carbons. So you can see pentane in that CH3, CH2, blah, blah, blah. I'm just going to redraw it though. So that's pentane. So for our uniqueness, we want to consider carbon first, then hydrogen, then the ratio. So what do you think pentane should be? I heard some C's. What do you think it is? I heard some B's. We have the B's versus the C's now. Well, let me tell you this. C is not correct. What's the difference between C and B? C would be kind of a first approximation, and then B would be a refinement of that. There's an issue with C that doesn't jive up here.
So for the line stretch that you drew, 1 would equal 5, 6, 4, and then 3 would be by itself. So that would be 3 structures. And so that's why B would be correct.
So carbons 1 and 5 are equal, 2 and 4 are equal, and 3 is its own thing. The reason C is not correct is because it's lumping 2, 3, and 4 into the same bin. And that is maybe the confusing part, because they're all CH2 groups, but amongst them, they're different. And why is that? Because again, if you imagine you're on this path, if you start at carbon 1 and go to 2, and then you look to your left and right, what do you see when you're here? A CH3, a CH2. When you're on carbon 3, which is also a CH2, you look to the left, you look to the right, your perspective is now different. 2 and 4 have to be the same, and then 3 has to be different because things change. So, do you know what lemmings are? Like that Disney movie? It's pretty gruesome if you look at the story behind it, but don't fall under the assumption that these first two numbers are always going to be equal. They will not. And there's a reason why they won't be. But in this case, there ends up being 3 unique sets of the hydrogens. And so what we'll do is just write those numbers here. Since 1 and 5 are methyl groups, that's a total of 6 hydrogens. 2 and 4 are methylene, that's 4, and then 3 is methylene. So that's how we get those ratios. So there's only one linear isomer for C5H12. Everything else now is going to be branched. So this question is asking you the total. So the total of each type of carbon, where a CH3 group is methyl, CH2 is methylene, CH is methine, and C with nothing is called quaternary. So we know that 1 and 5 are methyl groups, so there's 2 of them, so we can eliminate B and C. 2, 3, and 4 are methylenes, that's CH2, so there's 3 of those, that eliminates D. So there's no CHs or no Cs. And again, this was a question asking about the total number of each of those. So as you'll see, right now we're just looking at the Lewis dot stuff and classifying. It's one way of classifying carbons is by the attached hydrogens. We're going to see other ways when we learn more about what do these lines actually mean in terms of bonding. So this question states, another constitutional isomer of pentane is named as a derivative of butane. Can you figure out the structure and then what is the uniqueness set for it? So I'll start the drawing here. We have the 5-carbon pentane. Now we have to start with 4 carbons. And we have 1 more to deal with. So that last one, again, it can never go on the end because you're just going back up 1 level. So it's got to go in internal. So we'll shove it right there. So this is a butane derivative. And what do you think the uniqueness set is? I heard a D is in dog. Does everyone agree with that? So 4, 4, 6, 3, 2, 1. So when you look at the longest chain, it's 4 carbons. Carbon 2, I'm going to say has local symmetry. Because when you're on carbon 2 and you walk out to that methyl or that methyl, you see the same thing. So these methyl groups are the same.
Would it matter if you put the other carbon on 3 instead of 2?
So the question was if we did that. Those are the same thing, even though I've numbered the backbone 1 way. And I'll get into the nuance of the nomenclature when we learn the rules, but ultimately if you take the bottom one and rotate it, you get the top one. It's the same thing. And then the name of this is 2-methylbutane. So maybe I'll do some unicorn color stuff here. So we said D, right? So there's 6. There's the 3. There's the 2. And I'm going to run out of colors here. I'll have to do it in red. So there's the assignments of those ratios. Question?
Why would we consider for it to be, would the green to be bonded as a
So the question is, these purple ones are methyl groups. The green is a methyl. Why are they not equivalent? So again, it's when you're walking along that path and you're seeing the viewpoint of what things are bonded to. If it's different, then they have to be different. So ultimately, again, how does this relate? If you had a carbon NMR spectrum, you would see 4 signals. The proton, you would see 4 sets, and then they would integrate to that ratio. So we did pentane, 2-methylbutane, and now there's one more that's a derivative of propane, meaning we have 2 carbons to put in. So where should we put those carbons? Say it again. So we have to put them both on the 2 position. Remember, because they can't go on the ends. They both have to go on that same carbon. This is a derivative now of propane. And the name is called 2,2-dimethyl propane. So the chemical nomenclature always has this form. The end of it is the parent. The parent tells you the main functional group, that's ANE, an alkane. There's some information about the carbon count, and then anything in front of the parent are the substituents. Again, we'll review the specific nuances of this, but the substituents are methyls. There's 2 of them. That's where this di comes from. And then these numbers tell you where on the chain they're located. So for shits and giggles here, what's the uniqueness set of this?
2, 1, and 12.
So 2, 1, 12. So 2 unique carbons, 1 set of hydrogen with 12 in that set. So carbon 2 has no attached hydrogens. That's a quaternary carbon. Again, another layer of the learning lasagna. I'm always thinking about food. So the reason you want to know methyl, methylene, methine, or quaternary, again, is you're going to learn a lot of reaction conditions. And associated with those conditions are the functional groups they act upon, and then of that, the specific type of carbon or hydrogen they're targeting. Any questions? So again, please don't murder me on the course evaluations, because I teach the lectures out of the chapter order from the textbook. So I pick and pull how I want to order the lectures to tell a story sort of from the ground up, how organic chemistry is useful. And through that, we're going to start with hydrocarbons as the first functional group. The reason for that is hydrocarbons originate from fossil fuels, including petroleum, coal, and natural gas. Those are the raw materials by which everything else is made. I'm not a hater by any means, but oils produced from plants don't interest me too much, but that you can make stuff from those as well. So, BP or Shell or wherever, they put these big oil derricks in the Gulf of whatever you want to refer to it. They get these substances out, they separate them, and then they send them to other companies to start doing stuff with. Those are the building blocks. So, some more ways of classifying hydrocarbons. We use the term saturated, unsaturated, and aromatic. Saturated compounds have carbon-carbon sigma bonds. And again, there's some nuance to exactly how that applies, whether it's locally or for the entire molecule itself. But another way of dealing with that, maybe not today, but on Wednesday, is when we start talking about hybridization. Hybridization is when you have to consider atomic orbitals present in elements versus bonding orbitals present in molecules. There's a huge chasm between the two of those things to accurately describe reality. Unsaturated can mean a couple things. There's a carbon-carbon pi bond. That's a new functional group. Notice the difference now. These are called alkenes. So there's an E in the parent. Or there can be alkynes. There's a Y now. So alkanes, alkenes, and alkynes, those are hydrocarbons. And then aromatic compounds have rings. That's basically, you take a linear compound, tether the two terminal carbons together to make a ring, and then they have some pi bonds. So that's teaching that later today in Organic 2, aromatic chemistry. So these are the feedstocks by which we make stuff. We're going to learn reactions. And so take, for example, this is one of the first reactions we'll learn later on in Module 3, I believe, or 4. This is called a CH substitution. This is methane. It's nonpolar. There are the physical properties. So we can take that H atom and then substitute it for a chlorine. That's called a substitution. So H to C. Part of what we'll learn as well in this semester is not only the reaction, the conditions, but actually how does that happen? How do the electrons move? Is it 2 electrons moving? Is it 1 electron moving? Are there intermediates? What are the energy requirements for that? But as you can see, we're taking methane, a nonpolar molecule. We're now making chloromethane. That's polar. So why is it polar? Because chlorine has 3 lone pairs. It's delta minus, the carbon's delta plus. There's a difference in electronegativity. We now have a polar molecule. And then the physical properties change because of that. So let's look at these classes of hydrocarbons in relation to their molecular formulas, and then this thing called degrees of unsaturation. Your book may call this something else, index of hydrogen deficiency or something like that. The main point of this is right here. The alkane functional group will always have that form for a molecular formula. For every N carbons, there's 2N plus 2 hydrogens. A fact of that is there's no unsaturation in there. There's no rings or pi bonds. That means every carbon atom has 4 sigma bonds. An alkene is described as a functional group with a carbon-carbon pi bond. So when you remove a hydrogen atom from 2 adjacent carbons, then you back bond them through a double bond. That pi bond, that's called a degree of unsaturation. To do that, you have to remove 2 hydrogens, so now the formula is CnH2n, meaning there's 1 degree of unsaturation. The carbon now has 3 sigma bonds and 1 pi bond. Notice that the total still equals 4. We're never going to break that rule of carbon having 4 bonds. An alkyne, now with the Y, we have to remove 2 more hydrogens. So we have CnH2n minus 2. Because there's 2 pi bonds, that's 2 degrees of unsaturation. The carbon will now have 2 sigma bonds and 2 pi bonds. The last hydrocarbon functional group I want to introduce related to a degree of unsaturation that's not a pi bond is a ring. So whenever you see the word cyclo, that means there's a ring. And a ring is equivalent to a degree of unsaturation because you have to remove H2 from the molecule. So it ends up having the same molecular formula as an alkene. So there's 1 degree of unsaturation, but notice the difference now. There's still 4 sigma bonds to each carbon, but no pi bonds. So we're going to use this one quite a bit to figure some stuff out. the CnH2n plus 2. So let me just start with butane. And hypothetically, I want to remove 2 hydrogen atoms. Again, I'm going to do it in a logical fashion here. I'm just taking a hydrogen from carbons 1 and 2. I'm going to remove them and then form a pi bond in the place. So now that's an alkene. And so the name changes to 1-butene. So from that, I'm going to remove 2 more hydrogens from 1 and 2. Now that's going to be a triple bond. And that's called 1-butyne. So by alkenes and alkynes, I just hypothetically remove the hydrogens from carbons 1 and 2, but say you wanted to do it other places, could you draw other isomers? So that's something you can think about, draw on your own, see if you can figure it out. So the functional group name is telling you what's present in there. So ANE, everything's saturated. All carbons have 4 sigma bonds. Alkene tells you there's a double bond, meaning that the carbons will have 3 sigma and 1 pi bond, just between 1 and 2, not everywhere. So make sure you understand that. Then for alkyne, carbons 1 and 2 have 2 sigma and 2 pi bonds. So here's a table to sort of show you what I meant by these different isomers according to the functional groups. So the first column here, we have carbon count starting with 2, then 3, then 4, then 4 branched. So down column 2 here in alkanes, ethane, propane, butane, 2-methyl propane. Say we wanted to now make cycloalkanes of that carbon count. So notice here you can't do that. You can't have 2 carbons and make a ring unless you're dealing with like some multi-dimensional math or something. 3 carbon atoms, you can make a ring. So propane, 4 is cyclobutane, and then if we wanted to make a branched one of that, we could make methyl cyclopropane. So please follow the logic here. That column 1 is just carbon count. As you move across the functional groups, the hydrogen count changes. For alkenes, we have ethene, prop 1-ene, and then notice here for the, this is what I was talking about with the carbon 4 count. You can move that double bond internal to the chain. So in these, it starts at carbon 2, but notice there's 2 of them. So think about the differences between them. I'm not going to articulate that now, but the difference matters. And then you can make a branched one from C4 as well. Alkynes, ethyne, this is called acetylene for all the welders, metal workers in the crowd. Prop 1-ine, and then the C4 count. So depending on where you put the unsaturation, you're going to get different molecules. Yeah.
Are we gonna go into like quadruple bonds or just stuff?
Carbon cannot form that. So we're not going to talk about quadruple bonds. That's more inorganic chemistry. You'll see a little bit later on, probably Wednesday and next Monday, the reason why carbon cannot do that. Because carbon's in period 2, and it only has access to S and P orbitals. And the way those things are hybridized does not allow it. When you get down to period 3, then you have D orbitals, and then you have a bigger toolbox to work with.
So basically, if it ends in A and E, that probably means it's mostly going to be sigma bonds. If it's E and E, there's probably going to be some sort of double bond in there. And if it's Y and E, there's a triple bond in there.
Yes.
Okay.
So the next couple slides here, I'm not going to spend too much time going over. They mainly give you some information to practice on. So from carbon count 1 through 6, you'll see when you get above 4, that's when you start seeing the constitutional isomers. So I think I stopped at 6. Because when you get to 7 and 8, the number of isomers you can draw increases quite a bit. I think 7 has like 15 or something, and carbon 8 count has like 35. So it's pretty easy to start redrawing the same thing you already drew if you're not logical about your approach. But over here, what you can do is look at these numbers as they're associated with the structures and see if you arrive at the same conclusion. And that's your way of practicing this. So can you read this name and convert it into a structural formula? Can you draw it? Then from that, can you classify the carbons, hydrogens, and the sets? So there's the answer key. Now go through the process of figuring that out. So that's for alkanes. The same exercise now for alkenes. Can you look at these names and draw them? Alkynes, same deal. So, this question was just asked, but when you're given a name and you look at the parent or the end of the name, it's telling you what the main functional group is. So a carbon-carbon sigma bond, that has to end in ANE. A double bond has to end in ENE, and a triple bond, YNE. So the answer here would be C. So if you had N equals 7, what would the total hydrogen count be for an alkane, an alkene, and an alkyne? So just shove the N into the alkane one. So 2 times 7 is 14 plus 2, that's 16. So that column kind of eliminates and gets you to the right answer. So 14, then you remove, or 16, you remove 2, that gets you to 14. You remove 2 more, that gets you to 12. Okay, so I think we have enough time to get through these last couple slides on this exercise. We'll start Wednesday with the orbital stuff. So I used to have a picture of Willy Wonka on this slide. Everyone knows who Willy Wonka is. So, there's this song, I'm not going to sing it for you, but, the chocolate factory is this place of imagination. And so these are my favorite sort of problems to do because I think they connect a lot of these concepts and allow you to practice it so you can be conversant in it. We have a molecular formula C4H6. How do we calculate the degrees of unsaturation? What does that tell us? And then from that, how can we start drawing structural isomers? How do we name them? How do we classify them? That's a way for you to practice the rules of building molecules. So we have N equals 4 from the molecular formula. And we have to figure out, for 4 carbons, what is the maximum number of hydrogens there should be? So 2 times 4 is 8, plus 2 is 10. So for 4 carbons, there should be 10 hydrogens total. The formula we're given is C4H6. So we're going to do some organic chemistry math. So we subtract that. The carbons have to cancel out. H10 minus H6 gets us to H4. A degree of unsaturation, as we said, is equivalent to a molecule of H2. So let's divide this by H2, and that's going to get us 2 degrees of unsaturation. So when you just look at this, you're going to say, yeah, well, whoop-de-shit, it's C4H6. But there's a lot of information contained in that, and we can use our imagination to start building things from that, as long as we're following the Lewis dot rules. Meaning you can't draw something with 5 carbons because it doesn't obey the formula. You can't start drawing, Texas carbons with 5 bonds because that's not allowed. So C4H6 has 2 degrees of unsaturation. So this is our nucleus to be creative here. Can we start drawing things? Can we classify them? Can we kind of figure out the name? And then if you really are bored and have time, you can then go look up those names and find the melting and boiling points to see how the structure affects the physical properties. So as I said, here is a table to sort of organize things. And it's arranged according to the carbon count. Sort of we're starting at 4, then we can break it down to 3. And then in the columns, notice the situation we're in. So 1 degree of unsaturation is a pi bond or a ring. But now we have 2 degrees of unsaturation, so we need the combinations of those things. So for, say, a linear compound with 2 pi bonds, that could be 2 alkenes or 1 alkyne, if we do that translation. Let's draw something. So say I have 4 carbons, and I want to now put in 2 pi bonds. So I could draw that. Then if I wanted to draw an alkyne, I could do that. Or I could put the alkyne in the middle. So let me number these, because sometimes alkynes can be confusing and students miscount the carbons. And I don't want you to think I'm a liar because I'm showing that H, and I said we never show them on carbons, but this is a special situation which it's easier to show it, to know that it's there and it exists. There's probably some other ones you could draw in there. I'll let you figure out that. What about the second scenario? We want a pi bond in a ring. So maybe what I'll do is draw the ring first. So 4 carbons. Now I want to put a pi bond in there. So that's called cyclobutene, and it does exist. And then maybe since we're running out of time, we have about a minute. I will give this 99-cent, no, it's 3 for 99, so 33-cent box of Mike's and Ike's to whoever can draw the compound with 2 rings in it. So who wants it? Come up to the board and draw a compound with 2 rings. We have a brave soul. He's coming down to it. How hungry are you? Congratulations. That is a compound that obeys the molecular formula and has 2 rings. So we're about out of time, but when you can go through the rest of these, start drawing according to the criteria, see if you can figure out the uniqueness of each and maybe what the name might be. Your exam opens in right now, so good luck.